Today, I'll be talking about fault detection and diagnosis for safety of mobile robots, which is the subject of my thesis which is the subject of my thesis done in Irstea of Clermont-Ferrand. Okay, after a brief introduction, I'll be talking about fault detection and isolation of mobile robots. I will show you our proposed methodology, some brief results before concluding. So as I said, I work in Irstea for the moment, in the ROMIA team, Robotics and Mobility for Environment and Agriculture. The thesis is funded by the region thanks to European funds. Okay, for agricultural robots and for mobile industrial robots, the robots are becoming more and more autonomous. They work for a long time in dynamic and unknown environments, and they do different functionalities. In consequence, faults become increasingly threatening. At each moment, fault may appear. So this is a small example here. I have a desired trajectory. Somehow, and for some reasons, my robot failed to do the desired trajectory. He is in this position here, but it is meant to be in this position. Fault detection consists on saying, wait a minute, something went wrong. Fault isolation, it's about knowing exactly why my robot is not in good conditions. What is the fault exactly? So fault detection and isolation FDI is a crucial task to maintain all of these, it's not very accurate, all of these functionalities. Moving on. In order to be applied successfully, a fault detection and isolation system must satisfy some requirement, such as real-time requirement, online requirement. It must cope with non-linear behaviors. It must be adaptable, and this is very important in agricultural environments, because today it's raining, tomorrow it's not raining. Today we have fog, tomorrow we don't have fog. The robots work in a dynamic and very variant environment. And finally, the FDI system must be revealing and reactive in order to help the operator to better accommodate the fault. Our proposition is first to design a flexible global system, FDI system, integrating multiple FDI methods, and to put the human in the loop by interacting with him and ensuring a continuous adaptation and improvement, potentially, of our proposed method. For test purposes, we have considered 10 faults split into 3 categories: sensor, external, and mechanical faults. This is the state of the art, a brief state of the art. It's not very exhaustive, but just to give you an example. Mainly, we have 3 categories of mobile robot, of FDI methods for mobile robots. Model-based, such as well-known Kalman filter and all of its variants, UKF, EKF, curvature, etc. Analytical redundancy, and etc. Knowledge-based, such as well-known PF or particle filter and its variant. Data-based, such as deep learning, neural network, etc. As you can see, each and every one of these methods suffers from disadvantages and is applied in some conditions. So one method is probably, it's most likely not sufficient to deal with the entire list of predefined faults. So that's why we thought about a hybrid diagnosis method englobing multiple methods that interact with human, as we said. Now, moving on to our proposition. This is our proposition. We have two parts, offline part and online part. In the offline part, first we identify. It's the conception phase of the robot. First, we identify what faults can we potentially have, or what faults we would like to treat in this FDI system. Second, we choose adequate methods from the list predefined. After we did all the modeling, all the technical job, in fact, tuning, modeling, collecting data, training, etc. And after, we move on to the online part. Now I'll be expressing the online part. It's composed of a hybrid diagnosis method and of HRIM, which is which is human-robot interaction model. For the HDM, it's simple. It's like this. It's simple in the form, but it's not well simple in application. First step is to evaluate each and every method that can deal with each fault in order to choose the most performant method that can detect a fault, and the best method that can isolate a fault, because detection is not the same as isolation, as we say. To ensure a good comparison, we have proposed, not totally, a performance indicator. This is a brief form. It is composed of 4 sub-indicators: detection, isolation, cost, and anticipation. This serves to ensure an objective comparison between methods. Now, the human-robot interaction module. It is composed mainly of a knowledge database which stores some standard data, pre-known, the history of decisions made by human, and the second part is CBR, or case-based reasoning, which is an algorithm to recall at each step the most valuable state from the knowledge database, and the human-robot interaction interface. How underneath that, we have this scheme. In the case where a fault is isolated, which means I know exactly where is my fault, what is the problem. I do a criticality study. I'll be not talking about that, we don't have the time. And then a solution is retrieved from the knowledge database thanks to the CBR. The human can validate or can propose another solution, and also all of its decisions will be stored in the CBR. In the other case, the fault is detected, but not automatically isolated. We can't have a 100% performance at all. Or in the case where the operator sent a signal, he said, wait a minute, something is wrong, but I don't know exactly where. In this case, we send the relevant information that we identify automatically depending on the actual state. And after, we help him with the history of his own decisions to isolate the problem. And after all, we adjust continuously our HDM, hybrid diagnosis method. It's HDM, not HMD, in order to maintain the performance of our HDM. So, moving on to application. First of all, the environment of application. We used mainly these 2 robots, skid steering robots, equipped with many sensors. The operator is considered as expert, it's me, and my colleague. We used ROS, as everyone. ROS permits us to intercept the signal sent by the sensor before sending it to the node, and that's how we can inject faults without ruining our system. For mechanical faults, it's a little bit more complicated. Somehow we hit the robot. Sometimes we hit the robot. We defined four contexts for testing: one indoor and one outdoor, and other context. So now for the offline part, I'll be talking about this. Potential faults, as we said before, 10 faults splitted into 4 categories. Relevant FDI methods such as deep learning, UKF, EKF, multiple model, adaptive estimation, etc. We did so many contributions here, but we don't have the time to express it all. After we modeled the fault, the robot, we collect data for AI. Okay, fine. All this is done offline. For the online part, this is a result of comparison of our faults in the case of one fault. I recall we do this evaluation continuously thanks to interaction with human. At each time, we get a feedback from our expert, intelligent, human, and we compare it to the decision made by our automatic algorithm. And that's how we get our evaluation. Secondly, this is the first form of HDM after the first evaluation. We have in the input data, we have post providers 1 and 2. 1 is for input for indoor data, and post provider 2 is for outdoor locations. Other sensors, laser, etc. We can see Kalman filter, deep learning, EKF, it's a flexible EKF for laser, etc. And everyone cope with detection or isolation of one or multiple faults. This is a prototype, just a prototype under construction of our graphical user interface made to interact with the operator. This is what the operator sees, in fact. Underneath that, we have all our schemes that I have explained in other slides. I will be showing you now a little video. It's quick, but I don't have all the control over video. I can't pause. So we will be seeing this interface, what the operator see in action. The robot, okay. The robot move. He don't move. That's a fault. I detected, but I didn't isolate the result. It works now. Here the operator demands some information. Here a fault is detected. Front right wheel blocked. And the algorithm helped me to propose a solution. The solution is to stop immediately. And I choose to interfere. Now everything is fine. It works. Now I send a fault signal. Here I have all the information that can help me. It's a prototype. Informations are not very speaking. He detects the fault again. Front right. It's me who injects the fault, in fact. And now I can validate proposed solution to stop the robot at that, and that's what I'm going to do here. So this is just a brief view of results. It's very satisfying. For laser perturbation, it's here. For GPS faults, it's in the up. We can see the ground truth, and in green is the actual detection. And this here is the command signal. So it's really challenging. So we have seen here our proposed FDI system for mobile robots. it can diagnose a list of FDI faults in real time. It is continuously enhanced thanks to interaction, thanks to intelligent interaction with human. In the future, it would be interesting to further implementation on different robots and different scenarios, much more complicated. It would be interesting to consider human experience level. We don't treat someone who knows a robot just like someone who don't know the robot. The information sent are not the same, and the value of his decision is not the same. And it would be interesting to apply this in multi-robot case. So thank you for your attention.
Thank you. Do we have some question for Mahmoud before going to lunch? No questions? Don't be shy.
Maybe you are hungry.
Sorry?
Maybe because we are hungry.
Even if we are hungry. I have just one question. At a given moment, you have to evaluate the fault detection system. So the expert should be back to check that fault detection is good or not. But the fact is that it will take a lot of time for the experts. So do you have an idea of how can we develop a validation process that permits to say, okay, my fault detection will be always good or not? Or is it difficult to do?
Okay. In fact, it's very difficult to evaluate without the interaction with human, because we are limited in terms of calculation time, we are limited in computation time, we are limited in the actual development of algorithms. But what we did here, we have tried to accelerate this interaction. We send only potentially interesting and only this information to the user, to the end user, so he can act quickly. And we send a suggestion thanks to the CBR, based on the history of his decisions. Otherwise, I think it's complicated for the moment to accelerate much the interaction. But in order not to disrupt all the time the operator, we interrupt him only in some cases when we are not very sure, when the criticality is not very high. When the criticality is not very high, in this case, we don't send information directly. We just validate proposed solution by the CBR, and at the end of the day, we will say, okay, Mr. Operator, we need to do a small briefing. What do you think of this decision? What do you think of this decision? And we gain time like this.